就是说okay, so previously so okay, so this proof just tell you is yeah, it's funny exercise. You can try to prove it. It's a funny exercise. And also there's I mean, so there's also like uh, some other kind of sanity check for this standard maybe. Not some sanity check. So for example, yeah, so actually I post into homework, but you can try to, it's not difficult. So these are homework questions then. So I will not tell you the answer, but yeah, actually I'm PowerPoint, but you can try to, yeah, if you don't know how to prove. So what this kind of sanity check is that if you write down like this as a definition of density matrix, then you can prove that you can prove this measurement axiom is consistent with your intuition. So what do I mean by intuition? Meaning that if I do this kind of measurement, meaning that I don't care about B, I only care about A. Once I do this measurement, right, the state will collapse into some other state. Then I want to say that this is the same as if I take the partial trace and do the measurement. So what is saying is that the partial trace and measurement somehow like they are commuted. So this is valid. So this is why this is why we define partial trace as what I just said. So this is just somehow a sanity check. 我又跟我讲，这意思是说我们刚刚讲有一个 axiom 是说你做一些 measurement 都 stable difference。那所以自然的说，你可以讲说，我 Alice 先做一个，我 Alice 就先去量我自己的 state。那我量完之后，这个 state 就会改变。那我 Alice 怎么量这个 state 跟 bug 应该无关。所以有没有 partial trace 理论上来说都没有差别。如果 bug 先，我就只看我自己的 state， 然后 measure 完跟 bug partial trace 完之后，我再 measure 这个行为应该是可以交换。就自然来说 ，Alice 不应该受到 bug 的动作影响。所以刚刚前面的那两个规则应该要自洽。partial trace 跟 measurement 不应该有矛盾，它应该是 consistent。不然的话就有问题了，不然的话就会出现一个奇怪的 action， 都比如说我 Alice 随便量，然后我就远距离讲 bug。我很远距离讲 bug， 如果说 in terms of probability distribution，this should be this。That proves it. And also this is also like added sanity checks that if you do the partial measurement of A and B, both it's the same as you do the probability distribution is the same as you do the complete measure. Yeah, these are some sanity checks. Okay, and okay, so the final like 5 or 10 minutes, and I would describe there's a more general math, especially only apply on density matrices, not just a unit term. This is called complete positive trace preserving math. Oh, there's somehow like complicated. So how should I describe about it? So for a constant state, right? So I know constant state is a vector. And in order for constant has this probability property, then I will allow. Then I must say that then I must define my linear transformation to preserve the norm of the vector. So and then by definition, this is a unitary. So if I define the unitary, so if I define the allowable transformation from a state to a state, then as a set, this set is exactly as a unit. But this is not true for density matrices, right? So if I want to study all the linear transformations such that I can map one density matrix into another density matrix, this is larger than the unitary transformation. Hopefully this is reasonable. 我再讲，比如说，大家为什么学？大家在量子力学里面学 unitary matrices，是因为要满足向量的长度 map 过去要是不变的。这个就是 unitary 的定义，所以你写下来，其实 unitary 就是这个定义就跟刚刚这个直觉是一样，就是长度不变的线性组，长度不变的线性变换就是全部加起来就是 unitary as a set, right? But in terms of then the matrices, then you can study that what's the set of linear transformation which maps density matrix to match density matrices. It's not just a unit. This set is larger than unitary. So maybe mathematical like this. So I can describe like this. So I can collect all the linear transformation. Let's say a set. Let's say I collect as all the linear transformation from one density matrix to another density matrix, row 1 and row 2. Such that row 1 or row 2 are many density matrices. This set is larger than the unitary. So simply speaking, as I just explained, right? So if you take unitary and then you go you row U later, then obviously this is a unitary matrix. This is a valid density matrix. So unitary is a particular case of inside this set. However, there's no simple description for this set. So this is why people define so-called complete positive trace reserve map. Okay. So let me explain what. Okay. So what is CBTP? Actually, you can represent very complicated. They can have very complicated physical meaning. Like they can, randomness, they can also discover subsystems. So it's not something I can just do a bunch of things. Now I can just delete some subsystem, and I can also add some fixed. Oh, so partial trace is also in CBTP. Okay. So why this is called complete positive trace preserving? This is simple. Okay. So the definition is linear transformation. So linear. And trace preserving is important because I want to make sure that my map in this map this guy, this C row, also be a density matrix, right? So trace positive preserved. And also its positivity is important because by definition, density matrices need to be positive semi-definite. So after this, it should be positive semi-definite. So 1, 2, 3 are very common. If it should be in correct. This is the definition. And so the weird part is probably the most weird part is complete positive. This is how it is. So from complete positive meaning that the definition is this. So what this means is that you take C, you tensor product with larger Hilbert space, biological series. Apply on this row AB for any composite state must be very good. So why we need this complete positive, not just positive. So intuitive, you can think that you want to say that your density matrix is not just density matrix itself, but your density matrix is some larger density matrices you do time trace. So you want to make sure that if you only your CBTP map apply on your small matrices should not violate this larger condition. So let me maybe something. So what I will say is that, right, suppose you have a map, right? So you have some map on your row A to some other density matrix, and it's this thing. But there's a possibility that this row A is not the density matrix itself, but it's a larger trace for other larger density matrices. So maybe your density matrix is there's a very large universe space, and you get your. Okay. So you hope your definition, you hope that if you apply C tensor with identity apply on a larger universe space, This guy should be also a valid density matrices. Because your C around yourself, but if you don't, then you don't modify environment. But this guy should be also positive. So this is why this is a stronger condition called composite positive. So hopefully you agree with this definition. 我讲一下，就是说你的 density matrices， 你就说你可能前三个定义是废，这个当然是自然，因为 density matrices 本身就 trace preserving positive. So the first 1, 2, 3 are like common, right? Should be true, should be good definition, right? So the where is this part? What is it? But we need this number for condition because your density matrices may be viewed as a okay. So we will prove that it can be viewed as a larger density matrices due to partial tracing. So this C is not just complete positive, not just positive on the low A part, should be complete positive for any tensor with larger Hilbert space. So this is called complete positive. Okay, so one non-trivial exercise to show that there exists a linear transformation which is positive but not complete positive. 就是这个 okay, so as an exercise, you can try to, or I mean, you can just simple. There's a simple example that is complete positive and it's positive but not complete positive. I think it's a swap. I think swap is just completely positive but not completely positive. Okay, and so people like try to. So people like try to classify all these kind of CPTV math. And it's very non-trivial theorem that I will not prove here, but you can find it. It's not. I think it's not textbook. This is standard, but the proof is not standard. So cross combination. So this proof say that any CPTV math C can be written as this one. With some weird entities satisfy this condition. Okay, so these are all cross decomposition. Decomposition is not unique. And if there's only one single cross operator, let's say there's no summation, there's only one, then this condition become like unitary. So you can view this CPTV as a somehow generalization of unitary if there's only one thing. So I don't have. I think for experimental physics, there's a more physical meaning about this cross decomposition. Yeah. So, but ideally, this yeah. So maybe I can say one. So for example, let me just provide one example of this, somehow this kind of CPTV map, right? I mean, I can write a density matrix and say, no, let's say rho is a single qubit. So let's consider single qubit. So I can write, for example, like this. There's a CPTV map like this, like 1 minus lambda with rho plus identity divided by 2. This is the CPTV map. And then it's so it's trace preserving. Okay, the reason is that if we take place, is we get 1 minus lambda because it's trace 1, and then say so we are working with single qubit, right? So the trace of identity is 2. Sorry. So you get which is 1. Okay, so this is an example. Satisfy trace preserving, and it's complete positive because this is a positive combination of two matrices. Yeah, and it's also linear. So what this channel or this kind of CPTV map meaning is that with probability of lambda, this state will be wash out, then become complete mixed state. But with probability 1 minus lambda, this state will be preserved. So physically, you can view this as somehow like a noisy channel. If I want to send quantum state into some noisy channel, then mathematically I would say that this state will have probability of 1 minus lambda to survive. But with lambda divided by 2, or with lambda probability, they become I divided by 2. I divided by 2 meaning that basically this state is basically this. Yeah, I just say it again. If you write down as matrices, it's basically this. So this state is called a maximally mixed state. Basically, this guy becomes constant. So one physical meaning of this equation is that your quantum state is passed into a noisy channel with probability 1 minus lambda. This is survive with probability lambda. Your density matrices will be completely destroyed and replaced by a complete mixed state. So this is a CPTB map. And you can prove that this state cannot be written as a unitary. It's not a unitary transformation. So, and this is also, you can do this as a cross decomposition, right? This is one cross identity. These are another cross operation. Yeah, so this is just a physical meaning。这个是意思是说，我随便讲一个例子，就是说，你给我电成 matrices， 我可以把这写成是这样，这是我的定义。那这个就是一个 CPTB map。那它有一个物理意义，就是说我有1减浪达的几率，这个 density matrix 是活着；我有浪达的几率，这个 density matrix 会变成 identity 除以2。那 identity 除以2的意思就是说1/2的0加1/2意义就是说这个 state 的所有资讯都没了。所以你可以想，这个 map 就相当于是我把我的 quantum state 送到一个传给别人，然后我要描述一个有 noisy 的 quantum，I want to describe a noisy quantum channel。Then I can use these CPTB languages. So this is why these languages are useful. Oh, okay. Now these are just a POV or something. Yeah, it's not. All right. So so now back to the we can study what's the single qubit density matrix, right? We are working with the high level thing. But what about a single qubit unitary? Or the single qubit density matrix, right? So for a single qubit quantum state is trivial, right? We already know the answer about 0 plus 3,000. This is for general single qubit. And satisfied with this. And then there's a phase equivalent, right? So in order to study the single qubit pure state is trivial that we already transformed it. But this is why I want to say this for a single qubit density matrix. Okay, so I claim that this is I claim that any single qubit density matrices can be written as identity plus some Pauli matrices with some vector R. This is what I want to say. Why this? So there's a one trivial fact in the quantum mechanics that any 2x2 matrices can be written as a linear sum of Pauli matrices. There are 3 Pauli matrices x, y, and z with identity, also added with identity. So for any 2x2 matrices can be written as linear sum with these 4 matrices. So hopefully it's and so now the question is that, but what's the coefficient for these matrices? So I know that any 2x2, it's not just density matrix, any 2x2 matrix can be written as A0 plus let's say R1x, R2y, R2. These I already know. But what's A0 mean? What's A0 for density matrix? So one thing I know is that Pauli matrices are traceless. So if I take this, then I take trace. Then all these x, y, and z are all 0. So I get A0 in the trace with identity matrices. For 2x2 matrices, 2P0. Okay, so A0 must be half. So so that means that I can write any density matrix into this F plus this x, y, and z. Then I just renormalize and I then put on. So it's here. Okay, and R is a three-dimensional vector. So up to this statement, for here, so these are proof. These are the simple. R is a three-dimensional vector are also over here. Okay. So the non-trivial proof, the non-trivial statement is that if this rho is pure states, then this R will be unit vector on Bloch sphere. So this is why Bloch sphere can also describe the density matrix for a single group. And if for mixed states, then this rho, the Bloch sphere, this R will inside the sphere. So this is another way that you can plot the density. You can plot yours. You have the visualization for your single group. So hopefully the same is clear. So why is it? So remember that. Yes, use this notation. So let's say I want plus identity plus nice. So remember that we have a proof that if rho is the density matrices, then if rho is a pure state, then trace rho square must be 1. Okay. So what's rho square here? Oh, so I get 1 divided by 4. Identity plus R times sigma. However, this guy is a matrix. 2 plus R times sigma squared. 这没有问题。一个 I 矩阵写这样，平方就长这样。And I think I prove sometime. This guy. This guy is R squared. You guys remember? So this is R squared times identity. Or R times sigma. Remember the proof? Okay. Okay, let me just here. So these are like common Pauli equations, but I mean I can really do it. So okay. So let's say R times sigma. What's this? What's this? Oh, okay. So it's RZ minus RZ, RX minus RY, RX plus IRY. Z is 1, 0, 0 minus 1, right? X minus 1. And so you can compute the square. Okay. Okay, I just put here so that you can easily see. Oh, by the way, so R must be real because density matrix is Hermitian. So yeah, you can prove R is real. So if you compute this, then you can see this RZ squared plus RX minus IRY times RX plus IRY. So you get RZ squared plus R squared plus RZ squared. So it's basically the density. And this is 0, 0. This is also density. Okay, you can see here and here. So for this another diagonal part, you get RX plus IRY times RX minus IRY, and plus minus minus. So you get R squared. So this is R squared times identity. Okay, but also notice that as I mentioned, Pauli matrices are traces. So if I take trace rho squared, rho squared, and I have 1 divided by 4, and the identity is trace 2, right? Plus 2R squared. Yeah, right. That should be like this. So if rho is a pure state, then this guy is 1. this means that R must be 1. The R square must be 1. Okay. Yeah, you can. Yeah, you can take a. This is like textbook, but the rows here and take row square. So the only thing you need to know is this R sigma matrix. So if you take a trace row square, this is 2, this is 0, this is 2R squared. So you get 1 divided by 4, 2 plus 2R squared equals to 1 if rho is a pure state. Then this will say that the absolute value of R is 1. Okay, and obviously that trace row square in general is less than 1, right? So that means that R squared is less than 1. Okay, so now you can, using this, right, you can happily plot your states. You can happily plot your states, whatever pure or density matrices on your blocks of field. Okay, so this is why if you go to like some YouTube, that people like describe your quantum state looks like on a sphere. So any state on a sphere is a pure state by this proof. And any state inside this sphere is a mixed state, as we proved. So for example, if you remember correct, this state is plus state. But this state. And this state is minus state. Sorry, it's a 1 state. Okay. Now this is and this is plus. So my question is that what's the states in the origin represent origin? What's the state? It should be a mixed state, right? Because it's inside spheres. But what's the state here? Not very simple. You just plot R equal to 0. You just plot R equal to 0. So this state is identity divided by 2, which is a complete mixed state. With half of 0, 0 plus half of 1, 1. So the coin, the classical coin, we probably have, you can tell, probably have, you can have is basically a state represented as at the origin of pure state, at the origin of this philosophy. Yeah, so these states are special, but it's basically classical states inside here. Okay, so this is just some cartoon, like some cartoon that go to YouTube. There are many videos about the philosophy. Yeah. Oh, sorry. So the proof is here. So actually, I just write down. Oh, so we just define a purity to be trace row squared, and that proof, the purity is half 1 plus R squared, and I spelled here. So this is the proof. This is basically all the proof on it. They get same as on the backboard, but I just have it here so that you can use it if you want to find a reference. 这个应该没有什么问题。这就是说，就按照定义做一做，然后把它写下来，应该就可以。Okay, so box sphere visualization, the north pole is 0, 0, and the south pole is 1. Equilibrium point is plus and minus. By the way, actually, it's not immediately. You need to see the definition. You need to write down the definition for each one. And the maximum mixed state is R equal to 0, and rho will be identified by basically it's a coin. I just. Oh, yeah, so these are just more detail. At pure state 0, you get rho is 1, 0, 0, 0, so your R becomes 0, 0, 1. Okay, so this is identity plus Z. Right? Remember Z is 1, 0, 0, minus 1. So if we take identity plus Z, you get 1, 0, 0, 0. So this is why 0 state become R equal to 0, 1. And then for the mixed states, it becomes identity by 2, so R is. Okay. And this is the example that I show in this lecture. Basically, you take a Bell pair, then you get a partial trace, that you get nothing. And you get basically complete mixed state. Okay. So okay. Oh, oh, okay. So this is the final theorem for these tensor matrices. And by the way, so we will only use these tensor matrices are like common languages, but with high probability that we will only use tensor matrices in this lecture. So after the next lecture, everything back to this one and back to the state. So this is a theorem that I think it's important, but somehow like textbooks, the usual quantum mechanics does not tell you. So this basically says that if rho is a pure state for composite A tensor B, then there is a way that you can make the orthogonal. You can like in general you have like two indices, right? I and J, right? But what this statement is that there is a change of basis such that you can always write as a I and I with lambda I, support lambda I. This is different from first. This is not related. So it's related to tensor matrices, but it's not. We'll see later. But what this statement is just tell you that there exists a change of basis such that you can represent psi any quantitative tensor only one extra or one family parameters. And this down I call the Schmidt coefficient. And there are further equals 0 and some equals to 1. Okay. This equals Schmidt decomposition. So so it's non-trivial. You can write any state into lambda I and I tensor I. And why we need to use this formalism? Because if you write your states psi in terms of these languages, then you can compute the partial trace easily. You can prove that your rho A will be just this, and rho B will just be this. Just take an I squared out I squared, not I squared. Okay. And the eigenvalue of rho A will be the same. They are all lambda I squared. Okay. So even subset A and B looks different, they're reduced density than identical set. They have the same eigenvalue. So this is the implication why this Schmidt decomposition is useful. Because it gives you a way to compute the pure states, the partial trace of the pure states over a tensor product system. Oh, okay. So this is just the exercise. Okay. So let me quickly tell you the proof. So this is why we need a so-called singular value decomposition. So let me so singular decomposition tells you that you can write any matrices in terms of the two different unit terms. Let me just recall, right? So since basically use this is a singular value decomposition. You can write any matrix in two different unit terms with additional diagonal matrix, which is the element is non-negative. Okay, so the goal is to prove that any pure states can be written as this. For some level chosen basis for A and B. I can use I, but it's actually different basis. Alright, so the first so the proof is very simple. Trivially that any state can be written as following this. I pick a basis, this is definition of tensor product. I pick orthogonal basis J and orthogonal basis K, I can write any state in terms of solid J, K, and J, B. This is the definition of the tensor product. And AI is just a E by D matrix. Right. Now I can apply my singular value. So I can say A is UDB, U and B are unitary, and D is diagonal with real non-negative matrix. So in terms of so I just decompose. So I can write my state psi in terms of JK, but it's basically UJITIBIK or IJK. So I have additional I.
What is the coordinate of these? Like UJITIBIK.
No, just using this.
Oh,
you just expand your singular value decomposition and connect it back to There you go. Yeah. Okay. Now finally you just change the definition of change the basis. So you get that the first I subscript A to be sum over Jij, and the IB for sum over K, and the non-I to be DI. And then you get two proofs. So it's basically just Trinity composition is basically one sentence proof. It's basically single value composition. And then there are also bases because this U and B are diagonal bases. Other than also unitary matrix there. And the non operator to zero by the single value. So this decomposition is trivial, it's a single value decomposition. Okay. And so basically, this tells you that single value decomposition is powerful that you can compute the partial trace. Yeah, and it's called the basis. Basis. Yeah. Oh, the one important thing is that there is a number. The number of non-zero coefficient is coefficient. Basically, this measures the degree of entanglement. The reason is that if there's only one non-zero lambda I, that means that this state is that some state tensor product with another state, and then this basically is product state. So that means that the number of non-zero should be number as physical meaning. Because if there's only one, then you get a product state. Hopefully, let's see. Oh, although this Schmidt number is invariant under unitary on A and B alone, right? So basically these numbers invariant, it's basically some invariant with the for this entanglement. So it should be invariant under your change of basis. Or you basically apply unitary. So suppose you apply unitary U on subsystem A, then after the state becomes extract. But you only apply on the I part, the A part. So if L is some unitary and Bob is some unitary, this decomposition still will be the same. So the number of non-zero element of this lambda I is invariant. Even you apply so basically this means that this number basically measures the entanglement between the two systems. So the still should be decomposition on the basis of A exchange. Okay, so key insight that is the number depends only on entanglement structure, but not the local unitary choice. So you can view this as somehow like linear algebra tool for its density matrices. Yeah, so okay, so finally I want to talk about this so-called purification. Okay, so yeah, forget about math. So the statement is so we have explained the partial trace, right? We have explained the partial trace. So what this statement says that if you give me any mixed states, there exists the pure states, which such that this mixed state must be the same as must equals to the partial trace of that pure state. So what this statement says is that you give me any pure state, right? You give me any pure state. Sorry, you give me any mixed state. Rho A. There must exist a larger Hilbert space. There exists a pure state here, such that this larger pure state here, rho A B, such that your rho A must be the same as partial trace of this.这个意思就是说，你随便给我一个 density matrices， 它一定可以被看成是一个更大的 quantum state，一个 pure state，在更大的世界当中，它就确定下来。这个概念是意思就是说，其实你也可以忘掉，就是这个 tool，why this tool is important. So this tool, if you have this purification tool, sometimes that you do a research, right? You're dealing with some density matrices. You can somehow like forget about density matrices and working with the larger Hilbert states, but only focusing on pure states. So this is why this tool is sometimes used. Let me just tell you this. So proof is just
a question. The small TRR, does it also mean the trace?
Maybe what? It's it's a partial trace.
Partial trace.
Yeah, for the okay. So this is the remaining space. Or the rest space. The A is your system, and what this statement says that if you give me any density matrices on your A part, there exists the larger space, from R, such that and this space live in the A tensor R part.
Okay.
So you partial trace the remaining part you get rid of.
Is there a notational reason why we're writing small t and small I?
No. It's basically. Okay. So the proof just very simple. Why? Because you know that we have this Schmidt composition. So so first I can by definition, right? I can find both A in terms of PI, A bar. Right? Then I can define my row. I can define first state A tensor R using this by copy the same Hilbert space. By larger by twice larger my original Hilbert space. So let me explain. So you have row here, right? You can define a side AR by somewhere I and the square root of P. Notice that PI is not negative. So I can take a square root of PI and I tensor with I. So this remaining space is somehow like just an original copy of Hilbert space, but larger. Twice larger.
And why do we not write subscript A for the second pi equation?
Oh, it's fine. Yeah, I just use it right. Yeah. So hopefully this is the reason. So just twice you just make a copy of original Hilbert space, and then take that same similar state, exactly the same basis, but just copy, and then do using a define state here. Okay, so this is a well defined policy. Okay, and so the remaining is to prove that if you take this state and do a partial trace, then you get go. Okay. Then this is one proof. So you start with here. And let's say you compute psi, but you get square root of pi from j. So you get ij. You get your A has I and J, right? And your R is also has I and J. But you take a partial trace on R, right? So this will force this I and J must be the same. Yeah, so this is the J equals to I, you get I. This is why I take a square root, right? So I get PI itself. Then I PI brings through H. So how do we same thing in your purification? This is called purification. So purification basically just hopefully the words. Yeah, you didn't see this, the meaning of this word. Yeah, so this is it. So this proof just tell you that you can forget about sometimes you can forget about the density matrices and we're only working with the pure state, but you need to pay a price, then you need to do the twice larger Hilbert space. And purification is not unique, but what this theorem proof tell you is that if you waiting to pay the price of twice your Hilbert space, then you can always make the pure state into the you can always make the mixed state into pure state. Yeah, what you pay 就是说，你如果愿意把你 Hilbert space 放大2倍的话，那你就可以只 working with mixed pure state, and forget about mixed state. This is what this theory tell you. this is not the best way to do the purification. Right? Maybe, I mean, if your original state is pure state, then you don't need purification. But this statement tell you that you only need to pay like you only need to pay twice larger your as your original human space. Then you can always do this purification. I mean, the proof looks simple. You just take a square root of it. Okay, so yeah, this is just some relation between this decomposition and purification. Okay, so yeah, it is yeah. Hopefully this yeah I will upload this problem, but hopefully this problem and this actually give you some overall of this data depends. The language of data management is somehow is seldom talked about in quantum mechanics because it is somehow more related to the quantum information, or you want to do some like experimental physics. Because in there's one thing I missed. So in original quantum mechanics, you apply unitary or you apply the Schrodinger equation. This kind of evolution always maps pure state to pure state. If I have a pure state, I take a unitary, I still get a pure state. Right? The reason is this is hopefully obvious. So if I take a rho which is a pure state, right? And after I do the unitary, that the density measure is here. Obviously that this guy, if I take a square, is the same as this is identity, right? So you gotta use square. And then replace with those. So unitary will not change rho square. So that means that unitary will only maps pure state to pure state. Because the definition of pure state is trace rho square equals to 1 that we just proved. So I mean if you believe Schrodinger equation or unitary dynamics is somehow like underlying in the quantum mechanics, then if my initialization is pure state, then I will always get a pure state. So in the original quantum mechanics, there's no mechanism such that you can map pure state into a mixed state. So this is why in quantum mechanics, if you open up Sakura or other textbook, usually they seldom talk about mixed state. Because there's no, in general, I believe in your quantum mechanics or from your learning experiments, there's no mechanism that you can map pure state to pure state. You can map pure state to mixed state. You always map pure state to pure state. So this is why mixed state is somehow like nothing. So yeah. So but indeed there's other kind of if you add noise or you do some experimental physics, there are like generalization of somehow so-called faster equation, which is different from Schrodinger equation, somehow generalization of Schrodinger equation. And in that case, you can mix. So this is why like if you know some high energy physics in black hole or something, that I mean it's just for fun, but if you heard some like high energy seminar that people will debate that whether black hole, whether if you want or whether this black hole dynamics can be described by a unitary transformation. Because somehow if your information gets lost, that means that you cannot describe by unitary transformation. So this is why there must, but the problem is that there's no like underlying mechanism for you to map pure state to mixed. So yeah. So either you are starting with this experimental physics or you do some high energy, very high energy theory, then you will you need to. In that case, you have a very complicated mechanism, which cannot be described by Schrodinger equation such that you get it. So this is why, okay, so this finish the description of